Okay, are we back? Great. So in chapter 7, we're going to talk a little bit about complexity theory. This is not the central topic of this course CS500. If you're interested in complexity theory, actually, I'm very happy in this case because this is my actual area of research. I don't really research in algorithms, but I'm a complexity theorist, P versus NP, and computability theorist. And there's a dedicated course, CS 422, on theory of computation, which delves into all these issues, the Millennium Prize problem. So if you want to earn $1 million and become famous for solving P versus NP, this is the course you may want to take, CS422. But CS500 is tailored around design and analysis of algorithms. So we only need to recap here in this chapter 7, with kind of an intermission chapter, about the basics of P versus NP in order to understand and explain for why in the next chapter 8 we will investigate approximation algorithm, and yet another way of analyzing algorithms, namely analyzing their performance considered as how good an approximation they yield. And so please stand by with me if maybe things become a little bit technical and theoretical here. So we're going to recall the famous complexity classes P and NP that constitute the Millennium Prize problem. We're going to look at some graph problems, specifically the Eulerian cycle problem and the Hamiltonian cycle problem, and try to compare their inherent complexity. And recall that complexity means the cost of an optimal algorithm. And the problem is, of course, that in complexity theory, we don't know what is an actual optimal algorithm. We don't know what is the optimal algorithm. That's exactly the gist of the P versus NP problem, right? So we will have to deal with the situation where we try to compare algorithms. We try to determine the computational complexity, the cost of an optimal algorithm without knowing what is the cost of an optimal algorithm. The same applies to when we consider another pair of problems over graphs, the edge cover problem and the vertex cover problem. And another pair of problems about graphs, the clique problem and the independent set problem. Then we will formalize a way of comparing such decision problems, comparing the computational cost, the complexity of these problems without knowing their computational cost. It's a very smart way of dealing with the situation that we don't know things and still we want to be able to talk about these things. And then we're going to consider two problems that will later be considered from the approximation perspective, namely the traveling salesperson problem and the knapsack problem. And these turn out to be NP-complete problems, and what that means is something we want to talk about today. Consider this chapter 7 as a means to provide all of you with a background that is necessary in order to fully appreciate the following chapter 8 on approximation algorithm. So thank you for joining this poll. Thank you for helping me tailor this course. So if you already know NP, then don't worry, you can maybe just skip over the rest of this chapter. If you don't know, then maybe you want to listen more closely. Okay, so we're going to consider decision problems. This is different from the online problems we've considered. in the last chapter in the decision problem, the output, the input is given in advance, as opposed to online problems where the algorithm is revealed gradually. And in the decision problem, the algorithm is supposed to answer with a bit or a Boolean, yes or no. Again, this is different from, for instance, online algorithms, where the algorithm was, for instance, to decide whether and when to make a ski purchase, or to decide which page to evict from the cache. This is not a decision problem. But the P versus NP refers to decision problems, and we will also need to consider optimization problems, because that's what approximation algorithms are about. And I'm going to say in a few minutes what is the relation between decision problems and approximation and optimization problems. So a decision problem is just a subset of finite binary strings, an infinite subset in general, but of finite binary strings. And imagine this to be a binary finite sequence of bits, for instance, some string in ASCII encoded as bytes and therefore as a bit string. And this is presented to the algorithm, and the algorithm should give an answer, yes, if the input string belongs to the set L, and no, if the input string does not belong to that set L, and then terminate. That termination is important, because otherwise the algorithm might keep running and may keep changing its mind, right? So it says yes, but keeps running, and maybe 7 hours later it says no, but the user took the yes answer and thus runs into problems, right? So, and we say that this algorithm runs in polynomial time if the number of steps performed are bounded by a polynomial in n, where n denotes the length of the input. Okay, and P is the class of all decision problems then can be decided in polynomial time. And observe that the different decision problems in P can have different polynomials. So maybe n to the third, maybe another problem can be solved in n to 100. But the important thing is that the exponent is some constant, which may depend on the problem under consideration, as opposed to exponential time algorithms, where the running time is allowed to grow exponentially, which means that the exponent is not a constant. The exponent could, for instance, be n, 2 to the n, but also 2 to the square root of n, like for naive sieve algorithm for primality testing, that's 2 to the square root of n, or 2 to the n squared. That's also considered exponential time in our setting, right? Only 2 to the n, that's not exponential time, that's doubly exponential time. Right, and exponential time algorithms are bad, as we all know. Polynomial time algorithms are kind of good. And what's happening in between? In between is this famous complexity class NP of all problems that can be verified in polynomial time. And what do I mean with being able to verify it? It means problems that are on this following formal syntactic form. So these are problems of the following form. It consists of all finite binary strings x. So let me highlight that. A set of all finite binary strings x, such that there exists another finite binary string y of length bounded at most polynomially in the length x, such that the pair x comma y with some form of delimiter between x and y belongs to another set V, think a verifier, where V is polynomial time decidable. So this is a rather subtle and confusing definition if you see this for the first time. So we're going to consider them examples to motivate that definition. But the point here is, if you're given X and supposed to decide whether X belongs to L, if someone provides you with such a Y, if you're given both X and Y, then by the very definition, it is polynomial time decidable whether this pair belongs to V. and therefore whether x belongs to L, right? So if someone gives you a y, then you verify that the pair satisfies this condition in polynomial time, and then you know by the very definition of L, since there exists such a y, that x belongs to L. But that's why it's called polynomial time verifiable problem. Things become difficult and hard if x does not belong to L, because how do you know that there does not exist such a witness? Y is called a witness. How do you know that there does not exist such a witness? Maybe a naive way is by trying all possible witnesses Y, right? But the thing is there are exponentially many witnesses, right? So Y is a binary string. If this binary string has length polynomial in the length of n, in the length of x, which we usually denote by n, and of course they are 2 to the n binary strings, so actually 2 to the polynomial of n binary strings of that length, so that they're possibly 2 to the n, an exponential number of candidate witnesses, which to verify, and only if none of them satisfy this property, then we can be sure that x does not belong to L. So this is kind of a one-sided problem, a little bit related to one-sided error in probabilistic algorithm, right? So if someone gives us a y, then we can verify and can say for sure that x belongs to L. If nobody gives us a y, then we need to verify, try all possible candidate y before we can safely answer that x does not belong to L. That's a kind of one way of looking at the class NP of why it's called verifiable problem. The original name NP refers to non-deterministic polynomial time, but I don't want to introduce non-deterministic computation that is too easy to confuse with randomized computation. So for pedagogical reasons, if anyone of you knows NP as non-deterministic polynomial time computation, this definition is equivalent, but I make a deliberate pedagogical choice to avoid non-determinism in this class, which is just a kind of intermediate chapter 7 in order to provide the background for the main chapter 8 on approximation algorithm. Okay, so now we have these 3 classes or family of decision problems, and we need examples, right? Otherwise, this is what some mathematicians called abstract nonsense, making a definition without example. That's pointless. So here's an example. So this is a subset of finite binary strings. First, we take all finite binary strings, and then we remove the following finite binary string, the string 10, 11, 101, 111, 1011, 1101, and so on. And does anyone see here, of you see here some pattern about the binary strings that we're removing here? So what is 10 in binary? What is 11 in binary? What is 101 in binary? What is 111 in binary? Make a guess. What kind of numbers are these here in binary? Right, so you've guessed correctly. These are the binary representation of prime numbers, and having removed them, this is a problem of testing whether a given number is not a prime number. So this is a complement of the primality testing. And if you recall, we've indeed considered 2 randomized algorithms for the complement of primality testing, namely algorithms that tell correctly whether a given number is composite, but when the given number is a prime number, the algorithm Miller-Rabin, for instance, might still say, no, the other way. When the number is composite, the algorithm might still say it's a prime number. So this is a complement of the primality problem that we have considered earlier. And it's formalized as a decision problem as a subset of finite binary strings. So given the finite binary string, if this finite binary string is not a prime number, then a decision algorithm should say yes. If the given finite binary string is the binary encoding of a prime number, then the algorithm deciding that set should say uh, yes. No, the other way around. I'm confusing. So let's first try to rephrase that problem as an NP problem. So let's try to reformulate it as a problem of this very form as an example and motivation of why this is called verifiable. I mean, what would be a natural witness for a number to be not a prime number? Well, if we're given a proper factor, right? So this is different here from the primality testing, where we have seen that in general a number is not prime, but it might be very hard to guess a factor because it's very unlikely, if we just guess all numbers equally likely, to run into a factor because the factors could be very rare. But here we're not interested in likelihood, we're only interested in existence. That's in one sense the main difference between randomization and NP. NP's, the non-determinism is not about quantitative probabilities, only about existence of a witness. And of course here, when a number is not prime, there exists a witness, namely a factor. So, and this is exactly the idea. We rephrase this as a problem of the set of all binary encoded natural numbers, such that there exists a witness, another binary string, which is a proper factor. So that y is a binary encoding of some number which divides the binary encoding of the string, input string x. So it is a factor, and it must be a proper factor. It must be not 1, and also it must be of binary length strictly shorter than x, which means it must not be x itself, that then it would be not a proper divisor, right? So it means we have reformulated the non-primality problem, the problem of being a composite number, as a problem in the form NP as a polynomial time verifiable problem. Because why is it polynomial time verifiable? Because this property, which corresponds to this, is polynomial time decidable. So the set of all pairs x and y, such that the binary encoding of y divides the binary encoding of x. This is our v, our choice of v in this case. This is decidable in polynomial time. We just need to check whether the binary coding of y divides the binary coding of x, which can be done easily in polynomial time. So this example shows that the complement of primality testing, question whether a given natural number is composite, indeed belongs to this complexity class NP. Well, nowadays we know that it is actually a polynomial time decidable, right? Remember, we had this polynomial time algorithm by AKS, which is not entirely practical, but still there exists a polynomial time algorithm with a running time which is roughly n to the 6. Okay, so times is up for today, and this we will meet again next Tuesday and continue talking about problems in these complexity classes P and NP. And remember, the purpose of this intermission chapter is to provide the background in order to appreciate chapter 8, approximation